Um, well, I'd like to thank the organizers for putting together this multifaceted and certainly inspiring conference. And I'm very happy to open with quantum materials and quantum magnets. Thinking a bit about entanglement in magnets, let's think what we are supposed to aim for. So the elementary constituents in magnets are, of course, magnetic ions in some host, typically an insulator. If there were no interactions between the ions, you would just have a non-entangled product states. That's boring. With interactions, you can think about ground states, and ground states can be very interesting, as we just heard. You can get local entanglement, like in random singlet states or in some quantum ordered states, or you can get long-range entanglement, spin liquids, RVB states that give rise to topological order, and then anions, and then their braiding allows you to do topological quantum computation. That's not the topic today. That will certainly be addressed by other speakers. What I'm going to think about is excited states about the ground state. Typically, say, if you go at high energy above the ground state, you have dynamics that generates massive and uncontrolled entanglement. That means actually thermalization. And even if you want to impede thermalization, like with many-body localization that we will touch upon, there's still entanglement. It's just slower and less extensive, but it is still there. And usually you want to avoid that. And what you want is that you get controlled entanglement. That means quantum information processing, and that means entanglement is happening when you want and where you want. That means you want local degrees of freedom that remain coherent as long as you want. That's the qubits, and then you want to entangle them when you want. And that means you want to have interactions on demand. And I will show you at the end of today's talk how we envision to do that in magnets. But first, I show you sort of a more condensed matter experiment where we actually detect that in certain random magnets, there are coherent islands, surprisingly coherent islands, and those you can use as quantum sensors to learn something interesting about dynamics in these random systems, and in particular about many-body localization or quasi-many-body localization. Then I show you that if you enhance the local degrees of freedom and you make go from non-Kramers to Kramers ions for the experts, you get interesting entangled states. And eventually I show you how you could actually control entanglement at the large state in a kind of platform for quantum computation. So the first thing is a joint work by theory and experimentalists. On the left, Manuel Grimm, that was my PhD student in theory, and on the right, Gabriel Aplis, student Adrian Beckert, who worked on this. In a nutshell, what we found is that in a completely randomly doped magnet, we find these gems of high quantum coherence, and we use them to find out about the dynamics of the less nice stuff around. And that dynamics is very interesting because it's interactions and disorder combined, and that realizes a system that has long not really been understood, dipolar quantum dynamics in a disordered system. So what is the material that I'm talking about? It's a rare earth doped insulator. So we take a rare earth metal from the blue line in the periodic table, and we put it in a dilute fashion into a host that is an insulator, an insulating salt. Why rare earth? These are interesting elements because they have a partially filled inner or F shell. That means they have a large magnetic moment. The Russell-Saunders coupling makes a big moment, but outside you have the 5p and the 6s shells that screen what happens inside, and that gives you very good screening, safe phono from other ions in the material, and gives very long lifetime. So if you want to look for coherence in magnets, better look at rare earths, right? On top of that, you don't have only the electron spin, but you also have the nuclear spin on the nucleus of the rare earth. And that couples via hyperfine coupling fairly strongly sometimes to the electron spin and gives you very sharp, long-lived hyperfine excitations. Now, this is not something new. People have been working with that for ages, but in a very dilute limit usually. So you may all know YIG lasers, random rare earth lasers, where you use these sharp lines to create optical excitations or to make microwave to optical transducers to store light information. You know, you can make an array of ions like that, come in with light, you store it in the excitation, and you can take it out later, and with that you construct quantum computers, etc. That's all exciting physics, but today we want to explore what happens when you make this stuff denser. Still not super dense, but maybe 1 in 1,000 and not 1 in a million or 1 in a billion of magnetic ions. So why is it also interesting? Because these magnetic ions have a fairly large magnetic moment, as I told you already, and that gives you relatively strong dipolar interactions between the ions. So even if they are not direct neighbors, they still interact appreciably, and that gives interesting many-body physics. Good. The concrete rare earth that we take is terbium. Why terbium? That is particularly interesting because, so we put it into an insulating host. The host is lithium yttrium fluoride. Yttrium is also rare earth, but non-magnetic. And you replace about 1 in 1,000 or 1 in 10,000 by terbium. So at this dilution, it's of course not going to order magnetically. It's far too dilute, but there is interesting magnetic dynamics, and that is what we are going to sense via quantum sensors that will come up. Now, why terbium? If you put an ion into a crystalline environment, the crystalline environment produces a potential, and that breaks the SO3 symmetry of the ion and splits up the JLS multiplet into so-called crystal field levels. And what is particular about terbium is that 2 of these crystal field levels lie very close together at a frequency separation of 30 gigahertz about, and that's a very convenient microwave frequency. And it's just for this reason that it's very convenient to work with, because you can use microwaves. Furthermore, so these are singlet states, so singly degenerate states, so they have no magnetic moment, unlike the JLS multiplet, actually. But what is interesting is, even though they have no expectation value of the magnetic moment, if you make a quantum superposition of these 2 states, you get the magnetic moment. And then if you let the wave function evolve, this magnetic moment will oscillate up and down. And it's only the Z component of the magnetic moment operator that has a matrix element in this lowest 2-level system. Okay, so quantum superpositions on these ions are actually magnetic. And that's interesting. Okay, now there's an extra complication in terbium. All these non-Kramers ions that have an even number of electrons have a nuclear spin, and the nuclear spin couples to the electrons, and that means that hybridizes these 2 levels. And so the electronuclear eigenfunctions have now a magnetic moment, unlike the electronic eigenstates had no moment, as you see there. But with the nuclear spin, you will get the moment, and that's usually undesired, because then the ion states couple to magnetic field noise, and that's not good. So what you do is you apply an external field to compensate the nuclear spin, and at least a part of the ions will then be nicely coherent, or at least more coherent than the others, and those we call clock state ions, because that's what you also do in atomic clocks. And now comes a very simple idea. So if you have this paramagnet with the 0 and the 1 state, both non-magnetic, if you manage with an optical excitation or microwave to make a superposition, a coherent superposition between these states, you create magnetism on demand, basically, and it will oscillate around very nicely. So you could just come in with microwaves and boom, you have your magnet there. But that's too naive, because actually this crystal field splitting, this delta, depends a bit on the site. And very soon, all your terbium are out of phase, and you will see no magnetization. But you all know how to remedy that. Then you have to apply a Hahn echo. You have to go, you went into the equatorial plane of the Bloch sphere, and all your spins that disperse on the Bloch sphere. But if you apply a pi pulse, you can refocus and you get your magnetization back as an echo at least. Not always, but as an echo, right? So you can rephase, and it tells you that the individual ion is still basically coherent. It's just decoherent because you have an inhomogeneous line broadening. But of course, that's not the whole story, as you all know. These ions interact with other stuff, with phonons or with other terbium, with other nuclear spins. And so there's a dephasing that you cannot remedy by the Hahn echo, right? There are two basic processes. There is relaxation, and excitation can relax to something else, or there's pure dephasing that just means that the energy of your excitation is fluctuating in time without the relaxation process. And of course, that's bad because then your echo is not good anymore. But that is also good because the degradation of the echo tells you what the rest of your environment is doing, and you may be interested in how fast your environment is moving, in particular if you want to know about dynamics in a complex quantum system, right? And that's exactly what we are interested in here. So now this lithium terbium yttrium fluoride is very interesting because it combines two things: interesting quantum dynamics, this dipolar quantum dynamics of the typical terbium ions, and good sensors that can sense this. How does that come about? I will explain to you in a second. But first, let's think, what is the Hamiltonian of our system? It's very simple. The sums go over all the terbium ions in the material. They have dipolar interactions, and the only dipole, the only magnetic moment operates along the z direction. So you only have an Ising interaction, the red part on the right. The delta part is just a crystal field splitting between the 0 and 1, and that's off diagonal with respect to the Ising basis, if you want. Or the Ising, the magnetic moment operates off diagonal with respect to the crystal field basis, right? And the pink piece you can basically neglect because that's the part that we kill with the clock state condition, okay? And what you see here is a simple transverse field Ising model, but with disorder because the crystal field splitting, the blue part, is disordered. It varies from side to side in such a way that the variations are about of the same order as the interaction. So you are exactly spot on where you want to be to study many-body localization. So you have a competition between disorder and interaction. If you had only disorder, you would say this is trivially a product state, an insulator, and nothing moves. But then typically with interactions, you would say, you know, thermalization would set in at finite temperatures. And then there was this interesting idea that if disorder is strong enough and the interactions are weak and short range and so on, you could actually impede thermalization and get to what is called many-body localization. And if that happens, that means there's little dynamics and little noise generated in the sample. And there are very, very few solid-state examples, or actually none, where this has been observed. And so ours is maybe the first where we have a glimpse at that. Second, if we can see that, because the interactions are actually not short range, but quasi-long range due to dipolar interactions, we have a glimpse at, we have the opportunity to test theories about interaction-assisted dipolar quantum dynamics. So there is an interesting mechanism how interactions eventually impede the localization. So all that is in this lithium terbium yttrium fluoride. Okay, so what we need, so we have the interesting dynamics that we want to test. What we need is find coherent qubits and then use them to sense the flip dynamics via looking at their Hahn echo, right? So what we did is just, or the experimentalists did, we look at the echo decay, Hahn echo, as a function of frequency. So we sit at the excitation frequency of these clock excitations. And what we find is that as we tune across the inhomogeneously broadened line, we find vastly different echo decay, you see. And what happens as you tune the frequency is that you're selecting different ions, namely ions that have either a partner close by, and then that's what we call a terbium pair of ions, or you have a typical single ion. So the red is a typical single ion that's not very coherent. It has a fast decay of the echo. But if you go to pairs, they are much, much more coherent, and those can be used as sensors, right? So why is that? Let me quickly explain why that happens. So you can have two basic sources of dephasing and excitation, and hop from one ion to somewhere else, and then it's lost. It's a decay process. Or it dephases because something happens in the environment. And you have to protect against those two things in order to have something coherent. Now, what happens in a pair is that because the dipolar interaction in the pair splits the excitation to the first excitation, you can have the excitation on the left or on the right, and you have the even and the odd superposition, so an entangled state actually on this pair, and that is just spectrally detuned from the excitation on single ions. So you suppress the resonant hopping to a neighbor. You can just not decay resonantly to a neighbor. So the lifetime is much better on these pairs. And indeed, if you look at echo as a function of frequency, of course, you see a big peak there on the left. That's the single ions, but it's very broad. And then as satellites, you see very sharp peaks that come from these pairs, nearest neighbors, next nearest neighbor pairs at different energy shifts. You can also look for Rabi oscillations. So you excite your pair and drive Rabi oscillations, and you look at the echo, and you see that this is very coherent for a long time. Now, it's not only the jump to other excitations that can dephase you. There are also nuclear spins that produce noise, and that's hard to fight against. You can do dynamic decoupling, but the best would have been to choose a host that has no nuclear spins in the host, and that is for the future. But at least it gives us a window to look for dynamic effects up to that time scale of a few microseconds that the nuclear spins set. Now, the most interesting thing that we want to see is the dephasing that comes from the terbium ions that flip around the pair. Okay, then you say, well, but actually, didn't we arrange the pairs to have no magnetic moment by adjusting an external field to compensate the nuclear field? So why do you sense at all what the neighbors do? So if you have a pair sitting down on the left and you have a neighbor and it flips, indeed, you don't see anything to first order in that dipolar coupling, but you see in a virtual exchange of an excitation that goes sort of in a circle. That's why you call it ring exchange. This ring exchange depends on how what your neighbor does, whether it's up or down. And when it flips, it changes that second order interaction, and that gives you a dephasing. So that gives you a subtle quantum probe of the dynamics of your neighbors. And so now we went back to all these echo decays, knowing all the channels that can dephase us, and we fitted that to extract actually the lifetime of the single terbium ions that are sitting around. And now we remember there are different nuclear spin states. So we focused on the one with -3/2. That flips the fastest, but still at the time scale that is much faster than the microscopic time scale that you would expect. And then if you go to another species that you can also just vaguely detect, the time scale is even much longer. It's at tens of microseconds, which is about 1,000 times longer than the inverse of the dipolar coupling. So what we see here is basically a quasi-many-body localization in the solid. So the neighbors are so slow because of disorder, despite the coupling, that we now see that in the echo decay, which is not as fast as it could be. And the second take-home message is we have this random doping. We see an extreme heterogeneity in not only the dynamics, as you see in these timescales, but also in terms of the coherence. So the pairs are much, much more coherent than the singles, and you have that all sort of living together in one sample. So in the remaining 5 minutes, I want to show you a little how we go beyond that. So far, we worked with non-Kramers ions, and that was a very simple object. We got something nice out. But in order to go towards quantum computation, you have to enrich the local degrees of freedom. So in terbium, we had just had this 0 and 1 state. They were both non-magnetic, and there was one matrix element, JZ, that was non-zero off diagonally. Now, to enrich things, you should go to Kramers ions, that are those ions that have an odd number of electrons in the outer shell and have a magnetic moment in all the states. And because of Kramers degeneracy, all the crystal field states come at least as doublets. So now you have 2 and 2 states, and you have many more matrix elements. That's much more interesting. And now we want to operate between the bottom states of a JLS multiplet, from the ground state to an excited JLS multiplet, because that has a good lifetime. And because there we have powerful lasers and therefore fast operation. Okay, so we did that. We took the same host, but instead of terbium, we put in erbium, which is a Kramers ion. And again, we see a fat peak in the middle. So these are 2 different concentrations. Look at the red one for the higher concentration. Then you see these satellite peaks, and again, they are very, very sharp. And what does that tell you? Now we don't have a nuclear spin to disturb us, so we are at 0 field. We see that pairs at the same distance always have the same coupling, otherwise there will be an inhomogeneous broadening. So that's important if you want to build a quantum computer, you know your couplings because of the positions. And second, the pairs are actually much more coherent than the singles because they are actually naturally clock states. They have naturally non-magnetic states, and that I want to quickly explain to you. So a single erbium, because it's a Kramers ion, always has a magnetic moment, and that's kind of bad unless you suppress magnetic noise by strong field or low temperature. But if you put two erbium together, then you have 2 times odd equals even. That's a non-Kramers entity, and that has non-magnetic states. And that means it has no magnetic moment that couples to magnetic noise. And therefore, that's a good coherent object. And what is particularly interesting about these pairs is that the eigenstates or the excited eigenstates on these pairs are interestingly entangled. So the 2 erbium ions are maximally entangled in an excited state. So ion 1 contains all the information about ion 2, like in a singlet state or a maximally entangled photon pair. But also what is interesting is that spin and crystal field degrees of freedom get entangled. So a single erbium has these 2 doublets, right, that we want to couple. Now we take a pair, so you have 2 times 4 level system, and you look at the pair Hamiltonian. So there is, of course, the crystal field term, that's the first term. And then there's spin-spin interaction that either preserves the excitation on the left versus on the right, or it flops them. That's the second line. Now there's a simple pair symmetry. If you take this ion and you exchange it, then the Hamiltonian remains invariant. And so parity under inversion is a good symmetry. There is also nearly a symmetry if you exchange just the spin degree of freedom or the crystal field degree of freedom individually, except for one term in this first upper right part of the Hamiltonian. Now, if you look, so there is one term that is not symmetric under this extra symmetry, and that tells you that spin parity and crystal field parity is not separately conserved. And so they're mixed. And now if you look at the eigenfunctions, or you can ask which term gives you this breaking of this extra symmetry, it's actually the difference of the G-tensor anisotropy in the doublet in the ground state and in the excited state. So if you look what is the G-tensor, it will differ. It's not just a multiple of each other, and therefore in the Hamiltonian you get the term that breaks that extra symmetry that I talked about. And now if you look at the wave functions on the pair, you can look at symmetric or anti-symmetric states, and they can be either symmetric and symmetric in the spin and the crystal field degree of freedom, or anti-symmetric and anti-symmetric. And if you have a small difference in G10s and anisotropy, you will admix one to the other, and that means that there is information in the spin sector about the crystal field sector, which is small if this upper term there in the anisotropy is small. Okay, so you get entanglement entropy not only between one ion and the other, but between spin and crystal field sector. And here is a plot of what you could get as a function of this anisotropy difference. And you see in erbium, in lithium yttrium fluoride, you get about 20% of the maximal entanglement between these sectors. How to use that in the future is still a question, but if you have larger clusters, then pairs, maybe something interesting can be done. If I have 2 minutes, I could flash now how we envision to go. Right. So I just want to flash some ideas of how we could go towards quantum computing with ions like that. What we need as a basic ingredient is a quantum memory, and that would be the nuclear spin on an implanted ion. Then we need strong B field and temperature to actually suppress magnetic noise. Otherwise, since we have to work with Kramers ions, otherwise we would dephase very quickly. But then we need fast gates on a single ion and on pairs. On single ions, you can do very fast gates if you have Kramers ions because of this G factor anisotropy. What is a challenge is the 2-qubit gate. And I can quickly show you how you do a 2-qubit gate. You basically activate your qubit. That means you transfer quantum information from the nuclear spin to an electronic spin by an excitation. And now you have your quantum information associated with the magnetic moment, which is electronic and which is large. And now there's a large dipolar interaction, and that you use to entangle your 2 qubits that you selected, pre-selected. Then you let this interaction work for a certain time that you time carefully, and you implement, for example, a C0 gate. We work that all through. You can do that, and you get high expected fidelities and fast gates, actually. You can also check that you can address single qubits if you gate, and you create an initial state and you can read out. So we are convinced that in principle we have a universal scheme that meets all the DiVincenzo criteria. If we get there eventually, it's an experimental challenge to implement that. And with that, I would like to conclude and give you the punchline. So we saw that even in a randomly doped system, you have very diverse coherence and dynamics, and you can choose the coherent islands to sense interesting dynamics. Then if you go to Kramers ions, which are more complex as an object, you get very interesting, coherent, entangled local degrees of freedom. And then if you use these Kramers ions and selectively address them and make them entangled, you can do quantum computation, hopefully in the future. Thank you very much.
Okay, question, a quick time for 2 questions. Yes, back there. Yes.
Oh, right. So you're right. Terbium, no, terbium comes with one isotope, but it has a nuclear spin, and the nuclear spin orientation is random. When I say I focus on that, I mean theoretically I look what the guys do, but now you have nuclear spin 3/2 a total. That's the only isotope that exists for terbium, right? Erbium is a different story, but terbium has only one isotope, and then you can only make one of them coherent, one of the 4 nuclear spin projections, you can make coherent, and those work pretty well, as you saw. But the others do their own thing.
Yes,
Yeah.
Peter?
So when it comes to the spacing of these, it seems there's a trade-off, but the further away you get, the weaker the interaction is.
Right.
Also, I think it helps in terms of preventing like phonon. What's the sweet spot of how far away you want to be?
Yeah, that's a very good question. So we are thinking in the range of a few nanometers would be sweet. So then the interaction is still fairly strong. So you have fast gates, and yet you can control the dephasing sufficiently. Yeah. No, I think phonon decay is probably negligible. I mean, you know, you need only during the gates, you need to excite to these excited states, and the phonon lifetime is much longer, and so that's a negligible part to the dephasing. What you have to worry about is that all the other qubits that are lying around there, they're still interacting somehow, and you have to make sure that this interaction is bounded. Ah, I see. We estimated that, and that's a negligible effect actually at low temperature.